Hello everyone, Assalamualaikum warahmatullahi wabarakatuh. Welcome back again to my lecture. Okay, so in the previous video, we talked about system with outdoor air for ventilation where the bypass is equal to 0. If you missed the video, you can check the link in the description down below. That one. Okay, so today we will learn about this one. System with outdoor air for ventilation where the bypass is more than 0. So first of all, what does it mean by bypass is more than 0? This one. If you can see this one, the one that I circled here, bypass. What happened is that some part of the air, this one, before entering this cooling coil here, will not be cooled down by this cooling coil. Some part of the air will flow through without being cooling down by this cooling coil. So that is mean by bypass equals to 0. So usually the number can be 0.1, 0.1.5 or 0.2. We've talked about this one in the previous lecture. So please check back the video. So the situation right now is bypass is more than 0 where we have this bypass. So please look back this one. So this is the bypass factor. This one. So let's this one. So this one is the bypass factor. The one that I talked about 0.1, 0.2 or something. So here, again, as you can see here, TS. TS here is this one. This one is TS. TBC is this one. TBC. If we put a measurement, if we want to measure, so the temperature before entering the cooling coil. One of your friend asked me, for the previous lecture, does TBC equals to TM in this condition? Does TBC here equals to TM? Yes, correct. TBC here is actually TM. Because TM here is the temperature before entering the cooling coil. So in this situation here, if we look at this flow here, so as you can see here, this one here, flow through this one. So this is an outside air. So this is the air coming from the inside, which is separated in two. One goes through to the environment, another one, cycle back, to this, return back to this cycle here. So this is also actually a mixture, between outside air and also the inside air. So here also this one is also equals to Tm. So to calculate sensible heat of the cooling coil, we must use temperature before and after cooling coil. So means that Tm minus Ts. So when the bypass is equals to 0, so what happened is this one. Ts here is equals to apparatus dew point temperature. But when the bypass is more than 0, means that some part of the air is not being cooled down by the cooling coil. So which is why this one, we refer to this part here. So Ts here, Ts here is slightly higher than TADP. So Ts will increase a little bit more because a part of this air here didn't being cooled down by this cooling coil. And this air will mix together with the air that is being cooled down by this cooling coil. Which is why Ts is slightly higher than TADP. And the cycle is still same. This one. So to calculate other properties like mass flow rate of the supplied air and everything, we are using the same equation. Okay, like this one. Okay, if you refer to ms to calculate this one, and ms, okay, to calculate the situation where bypass is equal to 0, still same. Okay, if we consider this one, okay, if we think about the temperature before the cooling coil here. Okay? Okay, yeah. So, the one that we want to learn, okay, the new one here is this one. Okay, where the differences between sensible heat of the cooling coil minus sensible heat of the room can be calculated using this equation. This one. Okay, where the MO here is outside air, mass flow rate of the outside air, and TO here is the temperature of the outside air. Okay, this one. So the latent heat also we can use the mass flow rate of the outside air. Okay, and then this one WO is the humidity ratio of the outside air. Okay, and another temperature difference between coil and room, we can also use this equation. Okay, HO here, the specific enthalpy of the outside air. Okay, and to calculate coil sensible heat factor, this one still same. Okay, so there are some basic equation, okay, that we need to understand. Okay, ms here is maintained for all situation. Okay, this one also maintained for all situation. Coil sensible heat factor also maintained for all situation, in all situation lah. Okay, and then others also same. Okay, sensible heat, latent heat, total heat. Okay, the way to calculate it is maintained. Okay, but the condition is slightly different. Okay, this one is bypass 0, bypass more. This one is bypass more than 0. Okay, so I forgot to mention about this one. This one here in the previous lecture. So because we have a different temperature and also different humidity ratio before and after the cooling coil, and also the different temperature and also humidity ratio before and after the room. Okay, so both of these has a different temperature and humidity ratio, which is why the sensible heat of the coil is not equal to the sensible heat of the room. Same with latent heat of the coil is not equal to the latent heat of the room. Okay, so please make sure to use the basic equation to calculate the sensible heat and also the latent heat, which is again this one. Okay, sensible heat, we use this equation, mass flow rate multiply with the temperature difference. Latent heat, this equation, and then multiply with the difference in humidity ratio. Okay, okay, so next, this one. Okay, the relation of tons refrigeration BTU hour. Okay, this one. So we have cooling capacity, okay, which is usually we write it down in kilowatt cooling capacity. But if we refer to the aircon template or something, sometimes they use tons refrigeration, sometimes they use BTU hour. Okay, so tons refrigeration here is the rate of heat transfer to melt 1 ton of pure ice at 0 degrees Celsius in 24 hours. Okay, so BTUH here is another value lah. Okay, the relation here is this one. Okay, so 1 TR here is equals to 3.5 kilowatt is equals to 12,000 BTUH. Okay. Yeah. So in the next lecture, we will try to do one example, okay, one question, okay, and we will try to solve it together, and hopefully you can understand this one very well. Okay, so see you again in the next video. Bye bye.